Hi, I'm Josh Krupis. I'm a senior electrical and computer engineering major.
This is Colin Binford, and I'm a senior mechanical engineering student.
Hello, my name is Trey Whitmer, and I'm a mechanical engineering student.
And I'm Chris Benner, a senior electrical engineering student and the student project manager for the Solar PV team. The Solar team's mission is to strive that access to reliable electricity should not be a hindrance to the kingdom of God. To that end, the Solar PV team designs and installs solar power systems for partners in the developing world. Last year, the team worked with the Living Love Children's Home in Olkalau, Kenya. The orphanage needed reliable access to clean water. In their current situation, they pumped water from their well using a three-phase AC pump. The Kenyan electric grid does not supply three-phase power, so they ran the pump with a diesel generator, which was costly to operate. The pump also had only one speed, which was so fast it would drain the well if run continuously. Our solution for their water supply was a brushless DC motor and pump powered by a solar PV array. The DC pump will run continuously while the sun is up and stores water in a cistern for while the sun is down and the pump is not powered. The speed can also be adjusted to avoid overdrawing from the well. The solar well pump is also more cost-effective over the long term than the diesel-powered alternative. Designing and implementing the solution for LLM required us to obtain considerable knowledge both about solar PV systems and about the difficulties of working in a foreign country in very different circumstances than we have here in the United States. A problem that the solar team has encountered throughout the past 5 years of overseas installations is losing this knowledge when seniors graduate from the team. To deal with this, the solar team has designed and mostly built a solar lab at Messiah and is writing an accompanying training curriculum. Using the solar lab and this new training manual, we hope to better equip future teams to serve our friends and partners around the world. One of the first steps to designing the solar lab was choosing the components to use. The four biggest pieces to a solar PV system are the panels, the charge controller, the batteries, and the inverter. The solar panels produce the electricity from sunlight, the charge controller manages the power production from the panels and the charging of the batteries. The batteries store energy to be used while the sun is not up, and the inverter turns the DC voltage from the charge controller or batteries into an AC voltage like a normal electrical outlet.
Now, I'm here to talk to you about the Solar Lab components that were chosen for the Solar Lab at Messiah College. This includes the solar panels, the inverters, the batteries, and the charge controllers. The solar panels chosen for the new Solar Lab at Messiah College are the Sharp 208-watt solar panels. These are monocrystalline solar panels and were chosen because they were the original solar panels from the previous system at Messiah College, so the team already had these panels in their possession. And although they're monocrystalline and a lot of these installments in the past that we have done have used polycrystalline panels, these panels can still help us see how a lot of things affect system performance, like different configurations or age of panels. The charge controllers chosen for the Solar Lab at Messiah College are the Outback FlexMax 80 and the Outback FlexMax 60 charge controllers. We chose two charge controllers because this allows us to use the charge controllers in master-slave configuration. The solar team already had the Outback FlexMax 60 charge controller, so we only needed to purchase the Outback FlexMax 80 charge controller. We want to have experience with using charge controllers in the master-slave configuration because we have installed systems in the past, such as the system at TCZ, that have used charge controllers in a master-slave configuration. The solar team decided to choose two sets of 4 batteries for the Solar Lab at Messiah College. We chose the Trojans 27 AGM batteries and the Deca AG31 gel batteries. And having 2 sets of different batteries in our solar lab will allow us to see how different types of batteries age. We also chose these batteries because they are on the cheaper side for solar system batteries, and they are the most realistic for the types of batteries that we'll be using in system installments in the future. The solar team has actually decided to use 3 inverters for the solar lab. We're using 2 Outback FXR 2425A inverters, and using 2 of these inverters allows the team to, like the charge controllers, run the inverters in master-slave configuration. The team has installed systems in the past that use inverters in a master-slave configuration, so that'll be a good experience for revisiting old systems or designing new systems. These inverters also give us experience with a pure sine wave output. The other inverter is an X-Power inverter, and this is a cheaper alternative to the Outback inverter and also gives the team experience working with a modified sine wave output inverter.
Next, I will be discussing the mechanical aspects of mounting the equipment for the solar lab. The team desired to create a design for mounting the system that maintains simplicity through the consideration of cost-reducing opportunities, and reducing the time to disassemble or alter the system while ensuring a safe working environment. The Solar Lab was chosen to be wall-mounted in the Solar PV team's workstation in Fry 70, as the system was desired to be permanent in location and easily accessible. A wooden backing painted black was used since it has a low value for electrical conductivity. In order to reduce the time to assemble, disassemble, or alter the system, and to provide the spacing necessary for wiring the system, each component was decided to be mounted with 2-inch offsetting brackets, as shown in the figure on the right. These brackets were designed using SolidWorks. To ensure each bracket was able to support the load of the respective components, SolidWorks finite element analysis simulations were created and safety factors were determined. An example of this is shown in the image on the left. The most logical positioning and the spacing required between each component for wiring was then determined, and the design was reviewed by the team's advisors and knowledgeable engineers. After this, drawings were created to begin the process of construction. The brackets were created in the shop using the sheet metal shear, the hole punch machine, and the sheet metal bender, as shown in the figure on the left. Each component was then mounted to the respective brackets, and the brackets were screwed into the wooden backing, as shown in the figure on the right. Lastly, both side walls and a retractable guarding system were implemented to create a barrier for when the system is not being used by the team. Thus, the mechanical mounting portion of the Solar Lab was complete.
At this point, I will be explaining our battery enclosure. Battery storage is also a major component of our Solar Lab. As the battery enclosure was designed, we focused on safety, ease of access, and regulation of temperature within the battery box. Thermal testing was done to find the amount of air circulation needed to keep the batteries from overheating, and a loading test was done to make sure the box could hold the weight of the battery. Following our basic designs, a final drawing for the box was created. It was meant to serve as a barrier that both protected the batteries from outside harm, as well as protected anyone near the box from accidental electrical shock as a result of touching the battery terminals. The lid was also designed to slide off, allowing for easy access to wiring within the box. This allows for easy rewiring, which will be critical as we test out different battery configurations and their effect on performance of the solar PV system. In the spring, we began manufacturing the battery box, in which some minor changes were made to the design. The holes cut for the fans were changed from a square shape to a circular one to simplify our manufacturing process. A breaker was also added to the battery box, and a subsequent hole was cut in the lid so that it can be accessed without needing to take the lid off the box.
Unfortunately, due to our current remote situation, we have been unable to finish wiring the Solar Lab. Instead, the team has spent the last month working hard to complete the training curriculum introducing new team members to solar PV systems. These are the topics covered by the training. After completing a section of the training, a new team member should have enough basic knowledge of that topic to complete an accompanying hands-on activity. In closing, we'd like to thank our project manager, Dr. Fish, all of the collaboratory staff, our loyal group of review panelists, and all of you who logged on to support the work we've done this year. Thank you.